Hello everyone, my name is Rafael, and in this presentation I will show the work that I've been developing with Professor Luis Fernando Marta, which is a new version of the structure analysis software Ftool that includes nonlinear, stability, and vibration analysis. I will present the software from a user point of view, as most of the theoretical aspects have already been presented in the previous edition of CILAMCE. So, to show the new features that are summarized in this slide, I thought that the best way is to run the program and perform some analysis. So let's start it. Here we can see the new interface of Ftool showing a simple model that's going to be used for the presentation. And the first thing we should notice is the new drop-down list for selecting the type of analysis. The first option is the default linear elastic analysis, and then we have the new types, the nonlinear and the eigenvalue analysis, which I'm going to start with. And after selecting the analysis type, some analysis options must be set in a menu that can be accessed on the right-hand side. For the eigenvalue analysis, there are two types of simulation, which are the buckling modes and the vibration modes of the structure. So let's start with the buckling modes. Then the maximum number of modes to be calculated can be set. I will leave it with 10. And after running the analysis, the critical load ratio corresponding to each buckling mode is provided. These modes are ordered from the lowest to the highest absolute value of the critical load. And the shape of each mode can be easily checked by changing the number of the displaying mode. As we can see here, the 6 buckling modes of this frame that has 3 degrees of freedom. Now let's change the type of analysis for vibration modes. We can see that the type of mass matrix becomes available to be selected. The first option is the consistent mass matrix, and the second option is the lumped mass assumption for the mass distribution. I will start with the consistent mass. And the results now show the natural frequencies and natural periods of each of the 6 vibration modes. The shape of these modes can be checked in the same way, as you can see here. The scale can also be adjusted so the vibration can be better visualized. Okay. Now let me show the results of the vibration modes using the lumped mass matrix. So when I change it, we can see that only 4 vibration modes are computed, since we do not consider the rotational degrees of freedom in this type of matrix. Of course, the values of the frequencies and periods are slightly different, as well as the shape of the modes, as you can see. I should comment that the eigenvalue problem is being solved with the Jacobi method, and it's working well for larger models also. So that was what I wanted to show for the new stability and natural vibration analysis. Now I will show the geometrically nonlinear analysis of this same model, but in order to do it, I will add a horizontal load in this node to destabilize the structure. And I will change the analysis type to nonlinear. And now, if we look at the menu of analysis options, we can see that the first option is to select the source of nonlinearity that will be coupled together. Currently, only the geometric is available, but there is a master student who is implementing nonlinear semi-rigid connections, and he's presenting the details of this work in another CILAMCE presentation. Then the solution method must be selected. There are several algorithms implemented for solving the nonlinear problem. I will choose the load control for this structure. Then users can choose the type of increment and also the type of Newton iterations. And finally, the numerical parameters for the nonlinear analysis must be calibrated. And the analysis can be initialized with the play button. Step-by-step feedback is provided at the bottom, with the number of iterations and load ratio for each step. It is interesting to show that with these control buttons, it is possible to drive the analysis. For example, users can go back and forth how many steps they want, and it's even possible to change the analysis options and parameters between the steps. Another feature is to visualize the results of any past step by changing the step indicator number, as you can see. And it works for internal force diagrams also. For example, if I go back to step 20, I can see the bending moment values of that step. And some other new features for results visualization are available on the Options menu. Here we find the option for displaying the deformed configuration as straight lines instead of interpolating nodal displacements as it was being done before. Okay, and the next new option is to display the internal force diagrams over the deformed configuration. In this case, the diagrams are plotted over straight lines. Okay. And the last option is to consider the local P delta effect when computing bending moments, but this option is not working yet, so I will not present it. Well, a really important aspect of nonlinear analysis is the history of the results. So we develop an environment for plotting graphs of the results, as I will show now. In this environment, a graph is created by providing a name and selecting the type of data to be plotted in each axis, such as displacements, forces, load ratio, and step number. I will select nodal displacement versus load ratio for this graph. After creating the graph, a curve is added by providing its name and data. In this case, I have to select the node and the degree of freedom of the displacement so that the equilibrium path can be plotted. There are many ways to customize the graph by adding legend, for example, and axis reverse, swap. There are also many other customization options available on the Properties menu. As we can see here, we can change basically any property of the graph. And there is also a property menu for each curve, where users can edit their properties and style and so on. Another important thing for the graphs is the possibility of exporting and importing data, which allow users to compare curves of different analyses, and it's done with these buttons here. Well, in a nonlinear analysis of frames, the discretization of the elements is very important to obtain accurate results. So a new tool was created to automatically discretize the elements. Here we can set the number of subdivisions, and then we select the elements that we want to discretize and just press one button. So this tool is very useful for creating models for nonlinear analysis. Now we can perform the analysis again with this refined mesh. And we will see that the results are slightly different by looking at the equilibrium path. I will create another curve for the same degree of freedom as before. And we have a blue curve which provides a more accurate result for the geometrically nonlinear analysis of this simple frame model. We can easily delete a curve or a graph. And that finishes the presentation. We are looking to release this new version as soon as we can. I hope you enjoyed, and I thank you for watching.